Well, good morning, everybody. We are going to spend the day today and we're going to wrap up the unit that we are currently involved in. Throughout this unit, we've talked about polarity, we've talked about intermolecular forces, we've talked about how those intermolecular forces affect the way that about how they interact and how they behave. And then more recently, we've talked about these processes of boiling and freezing. And then the last time in lab, we actually talked about how we can change the temperature at which a liquid boils. But throughout this time and with all of these things that we've been doing, maybe without knowing it, we've left a couple unanswered questions. Now, these aren't questions that you necessarily need to write down as you're taking notes, but they are certainly things that you want to think about because these are questions that we're going to use as we focus in on the answers and use these questions to guide our learning. So guys, as we've been wrapping up this unit, there are really two questions that we want to address today. One is this: in the phase change lab, we learned that when water boils, its temperature doesn't change. We talked about the idea that when water boils, the intermolecular forces are breaking, but the temperature doesn't change when that happens. But we also noticed that unless your thermometer wasn't completely zeroed, your water should not have got to 100 degrees Celsius. As a matter of fact, you can't get boiling water to 100 degrees Celsius here in Utah. So the question is why? Why does water not boil at 100 degrees Celsius? Now, guys, understand we did sort of touch on this briefly when we introduced the previous lab that we did, but we're going to get into it a little bit more deeply today. Then, guys, following that, the next question that we want to talk about is actually really the conclusion question to the lab that you did last time. So we found out that when we add salt to water, the boiling point of the water goes up. The question is why? What is going on at a molecular level that causes that boiling point to increase? And then we're going to find out that this phenomenon actually affects other things as well. So guys, what we're going to do is we're going to take these questions one at a time. You're going to find that the answers to these questions are actually very related. And so at this point, I would encourage you to perhaps start drawing pictures with me. And let's take a look at how this works. So guys, question number one. Why is it that water does not boil at 100 degrees Celsius here in Utah? Well, to talk about this, we need a beaker. And so if you want to take a second and sketch a beaker into your notes, it could simply be a box without a top. However you think about this. But then what we're going to do is we're going to put some water inside of our beaker. And guys, when we put water inside of this beaker, if you join me up here at the screen, you'll notice that these water molecules are moving rapidly, but many of them are able to jump out of the top of the beaker. And when they do, they move into the gas phase, and this is representative of boiling. Well, the thought then is this: as this water is boiling, what is it that is going on as the water boils? So what I would encourage you to do is this. Go ahead, and you don't need to draw the reds and the whites. If you just want to go ahead and draw some circles into your beaker, and these circles represent your water molecules. Now, guys, the idea is this. In order for these water molecules to boil, they've got to get to the point where they can freely jump up and jump out of the beaker. You could represent that with a big upward arrow. So, guys, the question then becomes, what is it that keeps the water from getting out? And we understand already that one of the things that keeps the water from getting out are intermolecular forces. That ties the water molecules together, and these intermolecular forces keep them from leaving. And then, if we have a liquid that has stronger intermolecular forces, it would be harder for that liquid to leave. So one of the things that determines the temperature at which water boils is the strength of the intermolecular forces. But that's not it. There's actually another factor that determines the temperature at which water boils, and it's this. Sitting on top of this water, there is actually a 20-mile tall column of air. So we have air pushing down from above, pushing down on the surface of this water. So literally, when you go outside and when you look up, there is a 20-mile tall column of air that is resting on you. And that air, of course, has weight. And so the idea here is that the weight of this air, because gravity is pulling down on the air, the weight of this air also keeps the water from boiling. And as a result, for the water to boil, these water molecules not only have to break their intermolecular forces, they also have to push up against the weight of the air that is sitting on them. If you understand this, that then allows us to get to the idea of why water does not boil at 100 degrees Celsius here in Utah. So let me try to explain this to you by using a picture, if this will let me switch. And it won't. And so this is going to skip, and then we'll come right back. Okay, so guys, it looks like this. We talked about the idea that there is a 20-mile tall column of air sitting on us at sea level. So guys, the idea is this. If we have a beaker of water down here, that beaker of water has 20 miles of air sitting on top of it. That air has weight, and that keeps the water from boiling. Now, let's say we could go up a mile in that column of air. And guys, understand, we're a little below this, but imagine that we could go up to an elevation of 5,280 feet. That's a mile high in elevation. We're more like 4,600 feet, but let's call it the same. Say in Orem, we are a mile up in the atmosphere. Well, guys, what that means is our beaker is now no longer at sea level, sitting underneath 20 miles of air. Our beaker is now a mile up in the atmosphere, and now there's only 19 miles of air sitting on the water in the beaker. And guys, 19 miles of air weighs less than 20 miles of air, and as a result, the water boils at a lower temperature. And guys, understand, this just continues. So, for example, if we're in Utah, water boils at approximately 96 degrees Celsius. Of course, at sea level, it boils at 100. Move up a mile, boiling point goes down to 96. Now, guys, what if we keep climbing? Well, if we keep climbing, the boiling point continues to go down. And guys, as a matter of fact, at the top of Mount Everest, water up there boils at 68 degrees Celsius. It's barely warm enough to cook your food, which is actually a problem that high mountain climbers deal with. But guys, as we continue to climb, the boiling point just keeps going down. As a matter of fact, you can actually boil water and find the temperature at which it boils, and from that you can figure out your altitude. Kind of an interesting thought. So guys, this is why water does not boil at 100 degrees here in Orem. So that then brings up an interesting follow-up question. What if we wanted to make water boil at a higher temperature? So guys, if we wanted to make water boil at a higher temperature, there's really a couple things that we can do. And these are things that you want to include in your notes. So let me slow down because you will see this on the test that you're taking next time. So guys, the question is this: what could we do to increase the boiling point of water? So the first thing that we could do has to do with increasing atmospheric pressure. So guys, water in Utah boils at 96. What if we wanted to boil at a higher temperature? Well guys, what we could do is we could decrease elevation. We could go down to sea level, and then water would boil at a higher temperature. And that certainly would work. But guys, what if we wanted water to boil at a higher temperature here in Utah? Well guys, we can actually do that as well. And what we can do is we can create a high pressure environment. And again guys, I'll give you a second to scratch this down. But again, the other thing that you can do to get water to boil at a higher temperature is you can create a high pressure environment. And if the pressure is higher, then the water will boil at a higher temperature. So how do you do that? How do you create a high pressure environment? And guys, interestingly, the answer is an Instapot. That's exactly what an Instant Pot does. So if you've ever taken one of these things apart, you may know that down here we have a bucket. And what you do is you put a little bit of water in that bucket. And then what you do is you screw the lid on the bucket. And then you boil the water. And guys, what happens is as this water boils, all of these gas molecules get up here above the water inside the bucket. The problem is they can't get out. And if they can't escape, more and more steam builds up inside of the bucket. And this steam starts pushing. Remember, gas molecules travel in straight lines. This steam starts moving around and pushing on stuff. And it pushes on each other and it pushes on the lid, but it also pushes back down on the surface of the water. And that creates more pressure on the water, and that makes the boiling point of the water go up. Guys, that's why we call these things Instapots, because they cook a lot faster. The reason they cook a lot faster is the water that is down here inside the Instapot is a lot hotter than 96 degrees Celsius. It gets well above 100 degrees Celsius in there, and as a result, it cooks your food more quickly. Now guys, understand there's a limit to this. If we allowed that pressure to build up too much inside the Instapot, this thing could actually fail and explode. So some of you may know that back here on the back of the Instapot, there's actually a pressure relief valve. And if the pressure builds up too much, it kind of leaks a little bit. You can hear it sort of go psst, psst, psst. And what it's doing is it's releasing a little bit of that steam so the pressure doesn't build up too much. But guys, that's half the answer to the question. What can we do to increase the boiling point of the water? Well, one is decrease elevation. But the other thing we can do is we can create a high pressure environment, and we do that with pressure cookers. This is actually what mountaineers do when they're up at high elevations and their water boils at low temperatures. They actually take pressure cookers, not Instapots. It's pressure cookers that cook on gas stoves, and they actually cook their food in pressure cookers, and that lets it get hotter. Okay, so guys, we're halfway there. We now understand that if we want to increase the boiling point of water, one of the things that we can do is we can increase the pressure. But there's another thing that we can do. We can make the intermolecular forces stronger. Now guys, understand we saw this with the alcohol and the water. When we were talking about alcohol and water, we said water has stronger intermolecular forces and therefore it boils at a higher temperature. That is not what we're talking about here. We are talking about taking water and making the intermolecular forces inside of water stronger. So how do we do that? How do we make the intermolecular forces inside of water stronger? And guys, the answer is interesting. You make a solution. You dissolve sugar in water and the boiling point goes up. You dissolve salt in water and the boiling point goes up. And guys, as a matter of fact, anything that you can get to boil or to dissolve in water will make the boiling point go up. So add that to your notes, that the other way to make the boiling point go up is by creating stronger intermolecular forces, and you do that by creating a solution. Then guys, let's talk about how this works. Give you another second to catch up with me. So how does this work? How does creating a solution make the intermolecular forces go up? Well, guys, let's talk about it. So let's look at what it looks like when a solution forms. So here we have a crystal of salt. And that crystal of salt is in water. And when salt dissolves in water, literally what happens is the water molecules come along like little tugboats. And these water molecules, in kind of a literal way, they actually throw ropes to these ions. Now understand, the ropes are intermolecular forces, but that's literally what's happening. These water molecules come along like little tugboats, and these little water molecule tugboats come along and they pull the salt crystal apart, because the intermolecular forces between the water molecules and the salt ions allow the water molecules to drag these ions off into solution. And you see, as the salt dissolves, more and more of these water molecules cluster around the salt ions, and as they do, the salt crystal dissolves. Now guys, if you're paying close attention, you may notice the way these things organize themselves. So remember when we talked about the idea of intermolecular forces, and we talked about polarities, and here we have the polarities of these water molecules. Notice that these are all the positive ends, and those are attracted to the negative chloride ions. Then guys, over here, these polarities are going this way. There we go. These polarities are going this way, and that means that the negative ends of the dipoles are attracted to the positive sodium ions. And guys, these intermolecular forces that form between the ions in the salt and the water are what allows the water to dissolve the salt. Now guys, this brings us to an interesting point, and definitely something you're going to want to include in your notes. So guys, when things dissolve, so what you want to write down is a heading of solubility. You see it there at the top. But it goes like this. Dissolving is all about intermolecular forces. So here's the rule. In order for something, a solute, remember solute's the thing being dissolved, in order for a solute to dissolve in water, the polar water molecules must be able to strongly attract the particles in the solute. In the animation we saw before, we had polar water molecules, the tugboats, throwing their lines, the intermolecular forces, to the salt ions. But guys, these attractions we know are strong. How do we know that they're strong? Because if they're weak, the stuff wouldn't dissolve. And so this then is what we can gain from that. What this means is if a substance dissolves in water, it must be polar, because that allows the polar water molecules to grab a hold of it. If a substance does not dissolve in water, it is not polar. And because it's not polar, the water cannot form intermolecular forces with it, and it doesn't dissolve. That's why oil doesn't dissolve in water. Oil is not polar. As a result, the water can't grab a hold of it, and it doesn't pull it apart and cause it to dissolve. So here's what we know. We know that when something dissolves, it's all about intermolecular forces. And in order for something to dissolve, the water molecules have got to be able to throw their ropes to it. They've got to be able to tie on to it. And that happens through intermolecular forces. But water is polar. That means that polar water needs something to grab a hold of in order to dissolve it. And so the only things that dissolve in water are things that are also polar, like salt. You have a positive ion and a negative ion. Those are polar things. Things like oil are not polar, and therefore they don't dissolve in water. Now guys, with this in mind, it actually gives us the beginning of a starting point to talk about why dissolving salt in water makes the boiling point go up. So let me pause for another second. If you need to pause the video right now, you certainly can. But we're going to go in a moment, we're going to look at another simulation of what salt looks like as it dissolves in water. And then we're finally going to be able to talk about why the boiling point goes up. Okay, so let's go ahead and move forward. If you needed to pause the video, that was just fine. But let's go ahead and look at this. So what we're going to do now is we are going to look at this same phenomenon, if you will, when salt dissolves in water. But instead of this being an animation, a cartoon, this is actually a simulation. This is actually what it looks like when salt dissolves in water. So you've got the salt crystal there, the greens and grays, and these water molecules come along and they rip this salt crystal apart. They're tugging and they're pulling, and these intermolecular forces are ripping this apart, and we have this salt crystal ripped apart by the water molecules and carried off into solution. Now again, as we look at this, we need to understand that these water molecules are able to grab a hold of these ions through intermolecular forces. We have polar water molecules over here, and we have a charged, in this case negative, chloride ion. And so these polar water molecules grab a hold of this negative thing, the ion, and that allows these things to carry this off. Now what we're saying now is that these intermolecular forces, these forces of attraction, are very strong. How do we know that these forces of attraction are strong? And the answer is, if they weren't strong, the salt would not dissolve. You know of things that don't dissolve in water. Take, for example, sand. Sand does not dissolve in water because the water cannot grab a hold of it. It's not polar enough. So we know for sure that when things dissolve in water, the attraction between the water and whatever that thing is has got to be very strong. This then leads us even closer to the answer to our question. And it goes like this. We are now ready to define a term. These are what are called colligative properties. This is certainly something that you want in your notes. Again, guys, we're chasing after the answer to the question, why does salt make the boiling point of water go up? But when we ask that question, what we're actually doing is we're thinking about something called colligative properties. And you need to know the definition. I would encourage you to write this down. It says colligative properties are properties of solutions, salt dissolved in water, that are determined by how much and not what type of solute particle is in the solution. Could be sugar, could be salt, doesn't matter. It doesn't matter what's dissolving. It only matters how much is dissolving. All right, now that you've had the opportunity to catch up with me in your notes, we're now ready to answer the question, why does adding salt to water make the boiling point go up? This is an example of a colligative property. It is a property of a solution that happens when we dissolve something in water, salt in water. Specifically, we are talking about what is called the boiling point elevation colligative property. Again, something to include in your notes. The boiling point elevation colligative property. Again, if you need to pause the video for a second, please do. But let's now explore the boiling point elevation colligative property. And it looks like this. This is a picture of a chloride ion dissolved in water. The water molecules are all surrounding the chloride ion. And we know that the forces of attraction between the chloride and the water are very strong. Again, how do we know they're strong? Because it dissolves. But now imagine this. Imagine that this were a beaker. And up here at the top is the surface of the water. And then imagine that this water molecule right here wants to jump out of the top of the beaker and boil. So again, we've talked about this. What is it that's keeping that water from jumping out of the beaker? Well, it's two things, right? It's atmospheric pressure. But we're done talking about that. The other thing that is keeping this water molecule from jumping out of the beaker is the strength of the intermolecular forces that are holding it back. Now do you see the connection? In pure water, where there is no salt, the strength of the intermolecular forces that keep it from boiling are water to water. But now we have stronger intermolecular forces because now the water is tied more tightly to the salt. And because the water is tied more tightly to the salt, it's harder for the water molecule to get out. And as a result, the boiling point goes up because it takes more energy to break the stronger intermolecular forces between the water and the salt. And guys, understand, this just keeps going. If you dump more salt into the water, the boiling point will just keep going up and up and up because there's more salt making even more stronger intermolecular forces. And that's what you saw in the lab that you did last time. You added 3 grams of salt, the boiling point went up. You added 6, it went up more. You added 9, it went up even more. So guys, this is why the boiling point goes up. The water is attracted strongly to the salt, and as a result, those intermolecular forces are harder to break, and that makes the boiling point go up. So we can summarize all of that. We can summarize all of that like this. Boiling point elevation. The idea is that if the solute dissolves, this is the reasoning. If the solute dissolves, if the salt dissolves, the IMFs are stronger in the solution. Therefore, these stronger attractions are harder to break. Therefore, the boiling point goes up. Let me give you a second to include this in your notes. And again, you can pause the video if you need. I will wait for a second though. So again, when you add salt to water, if the salt dissolves, the intermolecular forces are strong. And stronger than the ones inside the water by itself. If the intermolecular forces are stronger, they're harder to break, and the boiling point goes up. Okay, so now guys, we're ready to shift gears, because interestingly, that is not the only intermolecular force that we're going to talk about today. There's another one. And guys, this other intermolecular force has a whole lot more to do with our daily lives here in Utah. This is what is called the freezing point depression colligative property. So again, guys, scratching this down in your notes, the freezing point depression goes down, depressed, not elevate, depressed. The freezing point depression colligative property. So let's look at some images and talk about how this works. So guys, here's what we're looking at. Over here, we are looking at salt water. Over here, we are looking at ice. Remember that ice has all of this structure. It has all of these repeated patterns. They're locked in place. The structure of ice. But now, imagine this. Notice over here again, same picture. We've got a chloride ion, and this chloride ion is attracted to all these water molecules. Now guys, imagine if we want to take this salt water and we want to get it to freeze. Well guys, there's something you need to understand. When you freeze salt water, the salt cannot get trapped up inside of the ice. Guys, water molecules cannot freeze if they're stuck to salt. So these water molecules right here that are attracted to this salt ion, these guys cannot freeze. So in order for the salt water to freeze, these molecules have got to get away from the salt, and they have got to be able to come over here and settle down and freeze. Now guys, in order to do that, they have got to get even colder. What happens is these molecules over here that are attracted to the salt, what we have to do is we have to slow these molecules down even slower than 0 degrees Celsius. And when we slow them down even slower than 0 degrees Celsius, they can finally get close enough to each other that they can latch on to each other strongly enough to turn into this structure and leave the salt behind. But understand, in order for that to happen, we have to cool this down even lower than 0 degrees Celsius for them to settle down enough to get close enough to turn into the structure of ice. This is what we call the freezing point depression colligative property. So again, when we add salt to water, the water is attracted to the salt. But water has got to get away from the salt in order to freeze. In order to do that, in order to allow these guys to connect, what they've got to do is slow down even more to a temperature below 0, and this allows them to slow down enough to get connected enough to freeze. So the freezing point goes down below 0. But guys, here's the thing that's interesting. This works in the other direction too. If you take a crystal of ice and if you shove, oh, that doesn't show up very well, just a second. If you shove, whoa, that's a box. That's even worse. So guys, if you come into the middle of this thing, what a mess. Get rid of that. Guys, if you come into the middle of this thing and if you shove a chloride ion into the middle of this salt crystal, what's going to happen? Well, what's going to happen is all of these water molecules are going to get attracted to the salt ion. And what's that going to do? It's going to rip this structure apart and it's going to make this thing melt. Now, guys, this explains why we put salt on our roads in Utah, because it actually does two things. If the road is frozen, the salt rips the structure apart. Now, guys, if the water is still liquid, we don't want it to freeze. And so putting the ions inside of the liquid makes it harder for the water to freeze, and it freezes at a lower temperature. So salt melts ice and keeps the water from freezing. Again, guys, these two things together are what are called the freezing point depression colligative property. And it looks like this. So the freezing point depression property logic goes like this. If a solute dissolves, the intermolecular forces are strong. The same reasoning as the boiling point elevation. But how do those strong attractions affect ice? Well, it goes like this. These stronger attractions make it harder for the water to get organized and form structure. And because it's harder for these ions, for these water molecules to form structure, the freezing point goes down. So guys, again, I'll give you a moment to get this in your notes. But again, we understand that if something dissolves, its IMFs are strong. So, if you put salt in water, the IMFs are strong. These stronger IMFs make it harder for the water to latch on to other water molecules and form structure. As a result, the water molecules have got to cool down more in order to get organized and locked together, and that makes the freezing point go down. But then, guys, also the other is true. If you put salt on ice, the salt rips the structure back apart. So, guys, there you have it. Bringing this full circle, we now have the answer to our two questions. Why does water not boil at 100 degrees in Utah? It's because of air pressure. We are higher up in the atmosphere. The weight of the air pushing down on the water is less, and therefore it boils at a lower temperature. So again, what can we do to change the temperature at which water boils? We can change the atmospheric pressure. How do we do that? 1, we go down in altitude. Or 2, we create an artificial pressure environment. That's a pressure cooker. But then the other thing that we can do to change the boiling point of water is add salt. The salt forms stronger intermolecular forces with the water. Those intermolecular forces are harder to break, and the boiling point goes up. And then as a bonus thought, as you see on the screen, when we add that same salt to water, it not only makes the boiling point go up, it also makes the freezing point go down. Okay, so guys, this is where we are. We have now wrapped up this unit. You have a homework assignment. It's the last homework assignment in the packet. Understand that the answers to this are on the wall. They're also posted online, but here we'll just use the answers that are up on the wall. And so guys, the remainder of the day today is yours to work on this homework assignment. Guys, remember that we know how to do this well. We are going to get phones and things like that out of our space, and we are going to invest in getting this assignment done. Guys, please understand that if you do need more support with this, Miss Call is readily available. She'd love to work with you. And then guys, remember that we will not obviously be recording this assignment until I get back. But please trust that you have covered well this material relative to the test. But guys, please remember to study for this test. There's a lot of material. This goes all the way back to drawing Lewis dot structures, subtracting the electronegativities of the elements that are involved in the bonds, figuring out polarity, thinking about symmetry. That's the dots or the different atoms around the middle, linking that to more and less polar, linking that to behaviors. Guys, there's a lot to review for this test. Please don't walk into the test cold. You're going to need to go back through this material prior to the test. So guys, the remainder of the time is yours to get the homework done, and remember obviously to invest some time in getting ready for the test.